Friends, this is Dr. Yamuna KM, Assistant Professor of Chemistry at NSS College, Manjeri. I am here with a lecture on the quantum mechanical aspects of chemical bonding. The syllabus prescribed by the University of Calicut for BSc Chemistry students in the second semester from 2019 onwards includes a course called Theoretical and Inorganic Chemistry 2, covers 4 modules. The first 2 modules cover the fundamentals of quantum mechanics and the latter 2 are on the quantum aspects of chemical bonding. In this lecture, I will focus on the latter part, the quantum aspects of chemical bonding. I have clubbed the two talks, the two modules of the last part together in this talk, and I will focus on the core aspects prescribed in the syllabus. Okay, let's now move on to the lecture.
Okay, chemical bonding. Chemical bonding involves bond formation between at least two atoms to form a molecule, and this requires considerations about the attractive and repulsive forces within the system. That is, for example, when two atoms approach each other, there can be attractive forces between electrons of one atom and the nucleus of the other atom, and repulsive forces between same charges like nucleus and nucleus, electrons and electrons. The balance between those two interactions, attractive and repulsive interactions, determine the chemical bonding. A bonding occurs, a stable bond occurs when the attractive forces overpower the repulsive forces. And a very important consideration is about the kinetic energy of the moving electrons confined within these boundaries. And that is about the general view of chemical bonding. And according to quantum mechanics views chemical bonding as a process of spin pairing. For example, two atoms as shown here, A and B, combines to get a molecule AB. That process occurs according to quantum mechanics in order to pair the spins. Atom A and B, they have separately unpaired spins, and during the bonding they get a paired spin. So according to quantum mechanics, chemical bonding is a process of pairing of spins. Before going to the details of the quantum mechanical aspects of chemical bonding, we have to see certain approximations. Quantum mechanics is relies on Schrödinger wave equation. Our system is expressed in terms of wave functions, and the system is understood in terms of the solution of Schrödinger wave equation applicable for that system. Exact solution of Schrödinger wave equation is possible only in case of hydrogen atom. The higher systems are very complicated and the exact solutions are not possible. So a molecule contains at least two nuclei and a minimum of one electron. This system is quite complicated. Like for example, the hydrogen molecule ion is the simplest system of molecule, and the exact solution of Schrödinger equation for this is not possible. That is why approximations are proposed which helps to reduce the complexity of the system. There are certain considerations are restricting the system, and based on these considerations or based on the simplest system available, considerations are developed, ideas about bonding or features of bonds, chemical bonding are developed, and then for more complicated system, those features are extrapolated or adapted. That's how we can explain, or we can do the computations, quantum mechanical computations on higher or more complex systems. So approximations help reducing the number of variables. We will see one of the approximations, like certain things are fixed, or certain considerations or certain uh, restrictions are proposed, and based on this further calculations or computations are done, and this computations on the most simple system, on the approximated system, helps for further calculations. One of such approximations required as a fundamental for chemical bonding is Born-Oppenheimer approximation, which states nuclei, being the heavier particles, much heavier than electrons, their movement is very slow with respect to the movement of electrons. That is why nuclei are assumed to be stationary and only electrons are moving in their field. For example, in this case of two nuclei and one electron equivalent to the hydrogen molecule ion scenario, in this case, the distance between the two nuclei, these heavy particles, they are fixed, or the assumption is the nuclei are stationary and are not moving, and only the electrons are moving with respect to the nuclei. And within this consideration, we are reducing the complexity, we are reducing the requirement of considering the nuclear velocity, the position of the nuclei, etc. So a parameter called internuclear distance introduces, because the nuclei are kept at constant distances with respect to each other. And these electron wave function solutions are sufficient for further calculations, and such an assumption called Born-Oppenheimer approximation, such an approximation leads to the construction of a potential energy curve, which describes the potential energy variation of the system when the distance between the two nuclei are adjusted. For example, the x-axis here given is the internuclear distance, and as you lower down the internuclear distance like this, you can see that the potential energy of the system gets lower and lower and reaches a minimum here. That is the equilibrium distance. We can also call it equilibrium bond length, because that is the distance between the two atoms, at the lowest energy state. And if you further decrease the distance between the two nuclei, you can see that the energy drastically increases. And this potential energy curve, it is called a potential energy curve because our nuclei are kept constant in position, that is, they are not moving according to the Born-Oppenheimer approximation, and they don't possess kinetic energy, and what energy they possess is only the potential energy. That's why it's called a potential energy curve. And with this understanding, or with this approximation in the background, we can move on to explaining chemical bonding in terms of quantum mechanics. There are two approaches with the quantum mechanical idea. The first one is valence-Bohm theory, and the second one is molecular orbital theory. Both these approaches, the valence-Bohm theory, VBT or MOT, both these are constructed on the idea of wave functions. They calculate the wave functions of molecules, and they adopt different mathematical approaches, but results are often similar. But the point here is molecular orbital theory is more advanced, and that is why it is mostly used in quantum mechanical calculation or computational works. But still, the first Valence-Bohm theory and the proposed idea are still in use for calculations. Coming to Valence-Bohm theory, it was introduced by great scientist Linus Pauling and co-workers, and the key points of the theory I will just mention through. Electron pairs, we see that electron pairing is the important aspect of bonding in the quantum consideration. So, shared electron pair get localized in orbitals. Their movement is confined within a particular orbital. And spin pairing occurs by the overlap of orbitals, and this spin pairing the overlap of orbitals leads to the formation of sigma or pi bonds. We will see the details. And in order to explain the bonding in polyatomic molecules, a concept called hybridization was introduced. We will see the details now about the important features of valence bond theory. Atoms in molecule are brought together by pairing up of their unpaired electrons, and this pairing occurs by the overlap of orbitals, and it results in bonding. And overlapped orbitals, they have now paired electrons, one each from each nucleus, and they are shared equally between the two bonded atoms. For example, here you can see when two hydrogen atoms are combining to get a molecule, what exactly happens is the 1s orbital holding the unpaired electron of one hydrogen gets overlapped by the 1s orbital of the other hydrogen, so that the electrons are now paired. The s is overlapping, the 1s and 1s, the overlapping results in a pairing of electrons. And the features of overlapping includes the important ideas overlapping should be to a maximum extent as possible. That is called principle of maximum overlap. The higher the extent of overlap, the stronger will be the bond because the energy will be lower. And there are two types of overlapping, axial overlapping and lateral overlapping. That two orbitals of the same symmetry, they can overlap head-to-head manner along the axis to result in axial overlapping, and that results in the formation of a sigma bond because it is very similar to s orbital symmetry, a cylindrical symmetry it has. And the second one is lateral overlapping or sideways overlapping. Two orbitals lying parallel to each other can overlap sidewise. And axial overlapping, here are some examples. First one is two s orbitals undergo axial overlapping to get an ss overlapped new orbital, and s and p you get sp overlapping and p and p along the axis. This is normally represented by pz, that is lying along this axis. The pz orbitals undergo head to head or axial overlapping to get this kind of new system. And coming to lateral overlapping, px and py orbitals. Two px orbital, one from one atom and the other from the other atom. When they lie parallel or sidewise, they can undergo overlapping to get a new system. And this overlapping results in pi bond formation. And this, you see here, the new overlapped system, the new orbital system has got a nodal plane. Electron density is distributed above and below the nodal plane. And comparing the axial and lateral overlapping, we can see that axial overlapping results in a larger degree of overlapping than the lateral overlapping. So obviously the sigma bond is stronger than the pi bond. And here let's see an example of hydrogen molecule. Let's see the quantum mechanical approach. We will see some wave functions, we will see some solutions of wave functions, but we will not go for the detailed derivation or detailed mathematical procedure because the syllabus is restricted only in the expressions. So considering the hydrogen molecule, here in this example, the hydrogen molecule, the first hydrogen molecule H1 and the second hydrogen molecule H2, they two combine to give a molecule of hydrogen like this. So this is the scenario. We have already seen this picture. And what happens exactly when the two atoms combine to form the molecule is, according to valence bond theory, the orbitals, the 1s orbital holding the unpaired electron of the first hydrogen overlaps with the 1s orbital holding the unpaired electron in the second hydrogen. They overlap each other to get a new wave function. That is, the wave functions representing the orbitals, wave functions corresponding to the orbitals are overlapping. And here I am using the expression chi, the notion chi, to represent the atomic orbital wave function and psi to represent the molecular orbital or the wave function of the resultant overlapping. So chi 1s H1 represents the wave function of the 1s orbital or 1s electron belonging to the first hydrogen atom, and this one is the wave function of the 1s electron belonging to the second hydrogen atom. And now the molecular wave function, the wave function of the new molecule, is a combination of the two wave functions. And we know S is a cylindrically symmetrical or spherical orbital therefore it can undergo only axial overlapping, and only sigma overlap or sigma bond formation is possible in between the two. And the wave functions of considering the electrons, before bonding, the first electron belonged only to the first nucleus and the second electron belonged only to the second nucleus, second hydrogen atom. But when bonded in molecule, both the electrons are equally possessed by both the nuclei. That means chances of finding one electron on one or the other nuclei are equal. Therefore, we can say the extreme possibility. For that, the extreme possibility is that electron 1 from the first hydrogen is confined to the first nucleus, and electron 2 of the second hydrogen is confined to the particular nucleus. And the other extreme is the first electron belong to the first hydrogen now is confined to the second nucleus, second hydrogen nucleus, and Similarly, the second electron belong to the second hydrogen atom, now belong to the first hydrogen. In a molecule, you cannot say this electron belong to this particular nucleus or the other electron belong to the other. In a molecule, electrons are equally shared. So, the wave function, the total wave function now you can represent as a combination of the two possibilities because the two possibilities are equal. So combining these two, you can see I can return two combinations are possible, additive or subtractive. This additive or subtractive means either the overlap is in phase or the overlap is out of phase. The additive overlap is the in phase overlap and the other one is subtractive overlap. In this equation, I use this constant n because this is the wave function is normalized here. So I can write this expression using a normalization constant n. And now we will see the consequence of this additive overlap. That is, here in this black line is the atomic orbital wave function, the chi's, and the orange color is the molecular wave function, psi. So now you can see here, the psi comes from the additive overlap between the two cases, two possibilities, or two atoms actually. That is, this electron belong to this nucleus and the other electron belong to the other nucleus. And this electron belong to this nucleus, this electron belong to this nucleus, like that. So, the important thing you can observe here is, when added together, the electron density between the two nuclei, here are two nuclei, in the internuclear space, the electron density is higher than the atomic electron densities. On the other hand, if you look here for the subtractive or out of phase interference, that is, here the first orbital undergo overlapping by the second orbital but out of phase. In that case, in the subtractive interference, what you can see is electron density between the two nuclei at the middle of the nuclei, there is almost zero. It is zero actually. There is no electron density. You can see it here. So, in the first case, in the additive overlap or in phase overlap, the internuclear electron density is larger than the atomic orbital electron densities, whereas in subtractive interface, the internuclear electron density is lower than the respective atomic orbital electron densities. Therefore, we can say the first case, the additive interference is more probable or more favored. And seeing some important features like overlapping of symmetric atomic orbitals result in this, and an increased electron density as I said before, and it offers a cylindrical geometry around the internuclear axis. Coming to this one, it is a destructive or out of phase interference and overlapping of antisymmetric orbitals. That is why this negative results and it decreases the electron density. So the first case is more preferred. And looking at the potential energy curve of the two cases, the first case you can see we have already seen this pattern. There is an equilibrium distance, the equilibrium bond length is there at which the molecule forms the most stable scenario, and this corresponds to this one. The symmetric overlap, and here it is asymmetric overlap. You can see there is no such a real lowering of energy. So the case is not really realistic. That's it. And now we will see a case of pi bonding also, that is sideways overlapping. You can see here I took the example of oxygen molecule, two oxygen atoms. We know that electrons in oxygen are filled in px and py orbitals, like they are half filled, the px and py orbitals. So this is the situation in one oxygen atom, and here it is for the second oxygen. Those two orbitals lying along the axis can overlap axially, undergoing a sigma bond. You get a sigma bond formation here, and these orbitals, the one lying along this direction and this one, they can laterally overlap as shown here, and this results in pi bond. That's how we have double bond between two oxygen atoms in oxygen molecule. One is a sigma bond and the other is a pi bond. And taking the case of nitrogen, we have got all the three orbitals half filled in all the three p orbitals half filled in nitrogen atom. So the one set of p's, pz and pz undergo axial overlapping. Px and Px undergo lateral overlapping to get one pi bond, and the other set of P's undergo lateral overlapping to get the other pi bond. So, in nitrogen molecule, it is triply bonded nitrogen atoms. So, now coming to the idea of coming to the considerations for polyatomic molecules, that you have got more than two atoms in the molecule, a central atom and ligands or binding partners around. The idea cannot be explained by the conventional valence bond approach. We will see some important things, and before that, in order to explain bonding in this polyatomic molecules, the idea of hybridization was proposed again by Linus Pauling, and there are two considerations called promotion and hybridization. In order to promotion is followed by hybridization. That is the considerations for polynuclear molecule bonding. So, why the conventional valence bond approach failed? Two examples are there. First one, predicting bond angles. For example, if you take water molecule having two hydrogens around one oxygen atom. See, oxygen has got two half-filled orbitals here, 2py and 2pz. We would expect that this hydrogen having this one electron can pair with this 2p and the other hydrogen can pair with the 2pz. As 2py and 2pz are lying perpendicular to each other, that is they are 90 degrees to each other, that's why we would expect that the hydrogen water molecule has bond angle of 90 degree, but that's not the case. We know that the bond angle is larger than 90 degree. So how to explain this? Similarly, we know carbon is tetravalent, but look here, carbon has got two unpaired electrons in its 2p orbitals, 2px and 2py has got one unpaired electron each. It can bind with, here 2px can take one electron and 2py can take another one electron. So the valency is expected to be 2, but the case is not that. It is tetravalent atom, carbon. So in order to explain this anomalies and generally in order to explain the bonding in polynuclear molecules or polyatomic molecules, the idea of hybridization was evolved. And it talks about the mixing of wave functions of the same atom. Previously, we have seen when two atomic orbitals overlap, the wave functions of the two atoms overlapped or intermixed. Here what happens is the wave functions of the same atom mixes each other. There is intermixing of atomic orbitals centered around the central atom to form a new set of orbitals having similar geometry and identical shape. That is a process of hybridization. We will see it with an example of methane. The central atom is carbon here and carbon binds with 4 hydrogens. Here it undergoes a type of hybridization called sp3 hybridization. As the name indicates, it involves one s orbital and 3 p orbitals. We will see the details. Here, this is the configuration of carbon in the ground state. That is, 2s has 2 electrons, 2px and y has 1 electron each. But to be able to accommodate 4 hydrogens, 4 binding partners, the carbon needs to have vacant spaces. So, it undergo a process called promotion. The electron from this lower energy orbital get promoted to the higher energy 2pz orbital. And this is called promotion. It's an energy requiring process actually. We will see the details. And this set of orbitals, the 1 and 3p orbitals, now can intermix to get a set of sp3 hybrid orbitals. Now what you have is hybrid orbitals with different identity from the s or p orbitals taking part in the hybridization. Now the sp3 hybrid orbitals have similar energy and geometry features. They have got, as it is sp3, one portion s character and 3 portion p character, and you can see 1s and 3p orbitals. 4 orbitals took part in hybridization, therefore you get 4 sp3 hybrid orbitals. Now I have got a question. How would you explain the energy requirement for promotion? This jump of electron from this s orbital to the p requires energy, even though very small amount. It is compromised or satisfied by this because in the first state, in the ground stage, carbon can accommodate only 2 binding partners. Here you see it can accommodate 4 binding partners. This already provides the energy requirement for promotion procedure. And this is the case. The 4 orbitals S and 3p's undergo hybridization to give 4 sp3 hybrid orbitals, which are explained by respective wave functions H1, H2, H3 and H4. Here H1, H2, H3, H4 are the wave functions that I represent the sp3 hybrid orbitals. You can see with the normalization constant of half, each of this hybrid orbital wave function involves a linear combination of the individual orbital, either additive or subtractive. These are the wave functions. It is important to remember those. And these sp3 hybrid orbitals lie in a particular geometry, lie in a tetrahedral fashion in the space with a bond angle of 109 degree 28 minutes, and therefore this is the case. And you see it's a tetrahedral structure and the bond angle is 109.47 degrees. You can see there is a relation. See, if you make an arc cosine of 1 by 3, 1 by 3 is 1s character and p3 characters. The ratio of s to p is 1 by 3. Arc cosine of this ratio, negative of 1 by 3, will give you the bond angle. That is a very important relation to remember too, according to you, especially in the view of your exams and stuff. So what happens during bonding? Now we have got the intermixed atomic orbitals, the wave functions of the orbitals of carbon, the wave functions of carbon itself, they mix, that is mixing of orbitals of the same atom happens, hybridization happens, you get a set of hybrid orbitals. Now what is needed is, this hybrid orbitals need to be overlapped by the hydrogen 1s atomic orbital. That's what happens here. Like this, the hydrogen atoms 1s orbitals are characterized by the chi wave functions. And what happens is, each orbital, the hybrid orbital H1 overlaps with the chi 1s of first hydrogen to get a new wave function of the molecule characterizing the one of the carbon hydrogen sigma bonds. You see again an additive interference, and similarly you can see the second hybrid orbital overlap with the 1s wave function of the second hydrogen atom to get the second carbon hydrogen sigma bond characterized by the psi sigma 2 wave function. Like this, the 4 bonds, the 4 carbon hydrogen bonds are formed. Psi 1, psi sigma 1 etc. represent the wave functions corresponding to carbon hydrogen bonds. See, here the electrons are confined within the carbon hydrogen bond. See, this additive interference occurs or in phase interference occurs here because then only it leads to a strong or stable bond. And obviously, as we have seen, this additive interference leads to an increased electron density in the middle of the two nucleus. That is carbon and hydrogen here. And we will see another example, another hybridization, sp2 hybridization. 1 s orbital and 2 p orbitals take part in hybridization as in case of boron trihydride BH3. You can see this is the ground state configuration of boron here. I will just fast pass through this. In the excited state, after promotion, you get one electron from here jumping to here. So 1s and 2p are available for hybridization now. You get 3 hybrid orbitals characterized by these wave functions H1, H2 and H3. And the 3 hybrid orbitals lie along the corners of a triangle. So you get the trigonal planar geometry with 120 degree bond angle. And this hybrid orbitals, the wave functions H1, H2, H3 now overlaps with the chi wave functions of hydrogen atoms, chi 1s, chi 1s1, 1s2 etc. to get the boron hydrogen bond. And another kind of hybridization is sp hybridization as exemplified by beryllium hydride. 1s and 1p, this is the ground state electronic configuration. When promoted, you get a new configuration like this, s and p. 1s and 1p become half filled. So sp hybridization to get resulting in 2 new wave functions H1 and H2 for sp hybrid orbitals, and they lie linear to each other with a bond angle 180 degree. And now this sp hybrid orbitals can overlap with the wave function of the hydrogens, 1s orbital of hydrogen to get the beryllium hydrogen bond. And there are other examples, other type of hybridization. Here I show some examples involving d orbitals. Phosphorus pentachloride is a molecule involving sp3 hybridization of phosphorus, the central phosphorus atom, and sulfur hexafluoride involve sp3d to hybridization on the central sulfur atom, etc. That's about the bonding in polynuclear or polyatomic molecules. And now we can summarize the features of the valence bond theory. As I said in the beginning, bonding occurs for pairing of electrons, and the shared electron pairs get delocalized over a particular bond, and this happens by overlapping of orbitals, that is mixing of wave functions of different atoms in two ways, sigma bond and pi bond, axial overlapping and lateral overlapping. And for polynuclear molecules we have got hybridization, there is a mixing of wave functions of the same atom. The hybrid orbital wave functions overlap with the binding partner orbital wave function to get the particular bonds to form the molecule. That's the salient features or key points of the valence bond theory. And with this in mind, with this background, we can now move on to the more developed or advanced idea of molecular orbital theory. The idea was proposed by Robert Mulliken and his co-workers. As I said, it's a more advanced form of valence bond theory, advanced than valence bond theory, and the key points are listed here. Again, the shared pairing of electrons and the shared pairing of electron between the two atoms spread over the whole molecule. Remember, valence bond theory said the shared pair of electrons spread over throughout the bond. Here, the electrons are spread throughout the molecule, and this spin pairing occurs by a process called a linear combination of atomic orbitals, LCAO we call. Two types of molecular orbitals. The atomic orbitals are linearly combined to get new molecular orbitals, which are in two types, bonding and anti-bonding molecular orbitals. And there are sigma and pi orbitals. We will see the details, and there is a consideration called bond order, which is a useful parameter to understand the molecule stability and energy. So coming to the details, let's take an example of the simplest case, as I said in the beginning. Two nuclei and one electron, the hydrogen molecule ion. The nuclei are fixed to each other with respect to each other by the distance r, capital R. First nucleus and first electron, the distance is Ra. First electron and the first nucleus and the electron, the distance is Rb. And those distances are related with this equation. The distance Rb is related with the cosine angle, and the Hamiltonian for this system involves, we know this, the h cross square 2me mass of electron me, and del square is a differential, and this is the potential energy component. The potential energy component involves all the three distances we know, and the first two distances are nucleus to electron distance, and indicates the electron nucleus attraction, whereas the third component here, the capital R, this term indicates the nucleus repulsion. So these two terms gives the attractive interaction, and the third term gives the repulsive interaction. Now, in order to explain the system, we need to solve the Schrödinger equation. H psi on E psi. H psi will give the eigenvalue E psi. It's an eigenfunction, Hamiltonian. So, psi is the molecular orbital wave function. We started with the atomic orbitals, and we get the solution of this H psi equal to E psi, the Schrödinger equation, will give you the new wave function called molecular orbital wave function. And that process of forming the molecular orbital wave function by the combination of atomic orbital wave function, that is called a linear combination of atomic orbitals. We will see it. Molecular orbital wave function psi mo is formed by the linear combination of respective atomic orbital wave function. The first hydrogen atom, its electron wave function. The second hydrogen atom, its 1s electron wave function. These two combine linearly, additive or subtractive. That means in phase or out of phase. This combination or superposition will give you new molecular orbital wave function. Here I express this with a normalization constant because psi is a normalized wave function. The additive wave function, that is in phase superposition, will give you a new wave function called bonding molecular orbital wave function. Similarly, the subtractive wave function, subtractive combination or superposition or out of phase superposition will give you anti-bonding molecular orbital wave function, psi BMO and psi ABMO. And orbitals, the resultant orbitals with cylindrical symmetry are called sigma orbital, and those having a nodal plane are called pi orbital. This is the fundamental idea when we learn about orbitals. Coming to bonding molecular orbitals, psi BMO, as I said, is formed by the combination or the additive superposition of the two atomic orbital wave functions, and the probability density, it is the square of the wave function psi. You can express it like this, and when you expand it, see here, we expand this with the equation a plus b whole squared equals a square plus b square plus a component of 2ab. If you look at this expansion, the psi square, the first component within this parenthesis bracket indicates the probability density if the electrons get confined to first hydrogen atom H1, and the second term, the chi square, here is the probability density when this electron is confined to the second hydrogen atom. But look at the third term. There is a new third term. There is an addition. This is added. There is an addition by this term. That is, there is an enhancement in electron density, and that is why it's called overlap density. The overlap results in enhanced electron density. Like this, the two atomic orbital 1s orbital wave functions chi 1s, they overlap in an additive way to get a new wave function sigma 1s. See, the internuclear electron density is much larger than the atomic orbital electron density. And this is a constructive, and there is a stabilizing effect because the internuclear space has got larger electron density, and that has got a stabilizing effect on the molecule. Similarly, considering the antibonding molecular orbitals, they are formed by the out of phase or subtractive interference between the two atomic orbital wave functions chi's, and probability density, as we have seen before, we can see the first term is the probability density if the first electron is confined to first hydrogen. The second term, probability density if that particular electron is confined to second hydrogen. And the total is reduced by this term, 2 chi 1s and chi 1s H2. This total is reduced. That means electron density is reduced by this term. There is a lowering electron density in the middle point. Here you can see the first 1s orbital wave function gets subtracted or get superposed in a negative way, in a destructive way, or out of phase overlapping occurs to get a new system of sigma star 1s, it is written. And you see in between the between the two nuclei, or at the center position between the two nuclei has got zero electron density. That is, there is a node. You see, there is a nodal plane in the two resultant molecular orbital. There is a nodal plane, and it has got a destabilizing effect because in the middle there is no electron density. So these two can be affected by a consideration. For example, bonding molecular orbital, the idea is the electron density between the two nuclei is larger than the previous case. That means the electron density, electrons are pushed more towards the internuclear region. Whereas in ABMO, antibonding molecular orbital, here you can see the electron densities are more pulled away from the nuclei. They are more pulled out towards the outside. Here the bonding molecular orbitals are written psi or sigma orbitals according to the orbital shape or symmetry. And In case of homonuclear diatomic molecules, this sigma or pi are written sigma g or pi g because for homonuclear diatomic molecules, the orbitals have got a point of inversion. That is, inversion symmetry is there and it is called Girarder symmetry. So those orbitals having Girarder symmetry are represented by sigma g or pi g. Likewise, in ABMO, normally they are represented by sigma star or pi star, but they are also represented by sigma u or pi u, representing Ungerade symmetry. Ungerade symmetry is their asymmetric overlapping occurs. Out of phase, that's it. The phases are asymmetric to each other. That's why it's called Ungerade symmetry. You can see the energies here. This is the atomic orbital of the first hydrogen, atomic orbital of the second hydrogen. When they overlap or when they undergo linear combination, you get two new atomic orbitals. Two new orbitals which are called molecular orbitals. The first one with lower energy is the bonding molecular orbital, and this one here is the anti-bonding molecular orbital with an enhanced energy than the atomic orbitals. See, the bonding molecular orbitals has got lower energy than the atomic orbitals, more stabilized, and the antibonding molecular orbital have got larger energy than the atomic orbitals. So destabilized. And here you see the energy difference between the ABMO and atomic orbital is larger than the energy difference between the BMO and atomic orbital. So, in the physical chemistry textbook published by Atkins and D. Paule, there is a beautiful sentence describing this. That is, antibonding molecular orbitals are more antibonding than bonding molecular orbitals are bonding. It's very interesting, no? And here we will see some of the shades when certain orbitals are undergoing linear combination. For example, two 1s orbitals undergo constructive interference, constructive overlapping to get sigma 1s orbital with this shape, and destructive or out of phase overlapping combination will give you sigma star with a node in between. Likewise, px and px constructive overlap interference give a pi because this is a lateral overlapping, not along the axis. That's why it is pi px, and the corresponding destructive interference gives you pi star px with a node in between. Likewise, py and py give you, the constructive overlap gives you pi py, and the destructive overlap gives pi star py because they undergo lateral overlapping. And here pz orbitals lies on the same axis, they can undergo axial combination to get sigma pz orbital in the constructive interference and sigma star pz orbital in the destructive interference with a node in between. And coming to the electronic configuration in a molecule, that is, electrons are filled in an atom, electrons are filled in atomic orbitals, but in a molecule you don't have atomic orbitals. What you have is molecular orbital wave functions and molecular orbitals, and electrons are filled in this molecular orbitals. So now let's see an example of nitrogen molecule. It has got 14 electrons, 7 from one nitrogen atom and the other 7 from the second nitrogen atom. So these 14 electrons are filled according to the three fundamental rules of electronic configuration. That is, Aufbau principle, Pauli's exclusion, and Hund's rule of maximum multiplicity. And like in the atomic orbitals, electrons are filled here. That is, 2 electrons here, 2 in the next higher energy, 2, 2, 2 like this goes up. And this is electronic configuration, and this configuration is schematically shown as here in a molecular orbital diagram. This shows the energy variations, etc. And there is an important feature called bond order. That is defined as half of the difference between number of bonding molecular orbital electrons and the number of antibonding molecular electrons. Here this NBMO, the first term is how many electrons are filled in all the bonding molecular orbitals. Here is how many electrons are filled in all the antibonding molecular orbital. Take your pen and do this calculation. What you get is an interesting result. It is 3 here in nitrogen. And this three, you can relate it like this: nitrogen and nitrogen. Two nitrogen atoms are held together by a triple bond in the nitrogen molecule. That corresponds to the bond order. And you can have more information about the molecule from the bond order. I leave that task for you to find out the significances of bond order. And with this, we will summarize the molecular orbital theory. Again, pairing of electrons and the delocalization. The electron pair is delocalized not only on that particular bond but throughout the molecular structure, and that occurs by the sharing of electron pairs. Pairing of electrons occurs by linear combination of atomic orbitals. Remember, it is the mixing of wave functions on different atoms, resulting in two possibilities are there: additive or in phase combination, and the other is subtractive or out of phase combination, resulting in BMO and ABMO, pi and sigma orbitals according to the symmetry considerations. And molecular orbital diagrams give you a schematic representation of electronic configuration in the orbitals, and the bond order is an important feature giving you more information about the molecular structure or bond formation. That's all about the molecular orbital theory. So friends, we have so far seen bonding in covalent molecules. And ionic bonding is treated more like a limiting case of covalent bond between two entirely dissimilar atoms A and B. This is not to our focus at the moment. So here I am winding up. If you have got any questions or would like to give feedback, I am always happy to receive feedback. Please contact me on this email ID given here. And excellent two books on international level by two international authors. You can see here I just selected McCurry and Atkins. I would say Atkins is the Bible of physical chemistry. That's a wonderful book. You will see some wonderful text inside, and my favorite book always. And I took the images from various web pages, and I thank those web pages that I could obtain figures from. And I thank you for your attention, and I'm looking forward for your feedback and questions. Thank you very much.